you guys are almost there. So today we have Mr. Bosa from Metro. He's going to talk about dynamic assignment models and their applications. So I'm sure it's going to be very interesting. So enjoy.
Great. Thank you, Miguel. First off, I'm very happy to be here today. I was a student at Portland State at one point, and I actually took this seminar for credit, and I've audited it many times since then, and I always find it very interesting. So hopefully I can also provide a somewhat interesting presentation today. I am going to be talking a little bit about our dynamic assignment tools that we use at Metro. I'm going to give a little bit of an overview of what transportation modeling is, some of the tools that we use in our modeling, specifically those focused on the assignment process, and I'll give some, I really want to focus on dynamic tools or dynamic traffic assignment. This guy is obviously a big fan of it. My buddy took this picture at Disney World of all places. So, and then I'll show you some examples of how we use these tools and the types of data and analyses we can do from these tools. So I work for Metro, which is a large regional agency that has their hands in a lot of pots. They operate the zoo, they operate waste transfer stations locally, the expo center, the convention center, some art centers. They're responsible for managing the urban growth boundary, which kind of helps dictate what land use looks like in our region today and into the future. But primarily a lot of the work that I do is focused on our role as a MPO, or Metropolitan Planning Organization. So an MPO is pretty much a federally mandated organization responsible for coordinating transportation planning in large urban areas, or basically any place over 50,000 people. We are required by the feds to meet certain mandates in terms of air quality, and we also help coordinate transportation projects so we can distribute federal funding to those various projects in our region. I work for the Research Center, which is a department within Metro, and we're primarily responsible for providing data and analytics and certain like geospatial services to clients, both internal and external. And my particular department, Modeling Services, we basically build, maintain, and apply several models, transportation models and land use models. There's also some econometric models, some population forecasting models, et cetera. But I'm a transportation researcher and modeler, so I deal with the transportation models. Our models are typically used in regional land use planning, long-range planning. We're looking 20 to 30 years out into the future, trying to figure out what kind of projects we want in our region, what do we want our region to look like. We have a pretty large spatial jurisdiction. Our jurisdiction covers Clackamas, Washington, and Multnomah counties, and all the cities within those counties on the Oregon side. And then we also model what's happening on Clark County, on the other side of the Columbia River in Washington State. Even though we don't have jurisdiction over Clark County, that area has a huge impact on what's happening on our transportation networks here. We also are responsible for coordinating corridor studies, and these might be highway improvements that impact multiple jurisdictions. These could be transit system enhancements like light rail extensions or new streetcars. And then we also do some air conformity analysis. Typically when we're doing transportation modeling, we're really focused on comparing differences between alternatives. So we usually start with some baseline alternative, with some baseline network. This is our highway network, this is our transit network, this is our bike and ped network. And then we look at making changes to that to see what kind of impacts it has on transportation in the region. So you might add additional highway capacity for autos, or you might add additional transit service, or you might build a new multi-use bike path somewhere. So typically what we've done during this analysis is we've looked at differences between your baseline and your alternative. And the tools that we've used in the past have been good at showing us what are the difference in volume. So if you add highway capacity somewhere, how does that impact the number of vehicles using that particular location? How does it impact other locations, maybe parallel to that facility? If you build a new light rail line, how does that impact competing bus lines, et cetera? We also look at average speeds, average travel times, and then we've used these older tools to kind of identify where the trouble spots are. And just one metric we typically use are volume to capacity ratios. So how much traffic or how many vehicles are using a particular location relative to its carrying capacity. And if you get a ratio of like 0.9, that means it's a very congested area. And typically this has been fine. We've used references of like 0.9, 0.95. And we've always been able to kind of figure out ways to build our way out of congestion. So we can add additional highway capacity, or we could maybe add new transit service and kind of get around some of those trouble spots. The issue is, if you've been out on the roadways anytime in the last 10 or 15 years, is you've noticed that we have lots of trouble spots and they last most of the day. And we're getting to a point where building our way out of congestion is no longer realistic. One, there's really not the space to do it. Space is at a premium. We're a pretty built-out urban area. But two, there's not the money for it. It's expensive, and there's just not enough in the federal funding streams to provide new highway links or miles. The other thing is we're looking at emphasizing better management of the existing system. So how can we manage our better system, our existing system smarter? This might include technology strategies like ramp metering or variable message signs or coordinating signals. And then there might be some demand management strategies where you try to encourage people to travel at different times of day or take different modes. But it's basically getting more out of your existing system. And our current tools just aren't able to help us measure the impact of those newer strategies. There's too many nuances involved with those that our tools aren't able to pick up. So what we've had to do is look for new tools. And dynamic traffic assignment is one of those tools. So when I talk about transportation modeling, I know when I first got into the field, this is what I thought transportation modeling was. It looks pretty cool. You see the cars moving around. You see this great urban landscape. This is not a transportation model. This is a screenshot of SimCity. And you can tell it's not a transportation model because if you look at this intersection here, there's a whole lot of malarkey happening. All those cars just went right there. Of course they would crash. And cars are moving on green and on red and every which way. So it's a pretty cool animation, but it doesn't really help you with your analysis at all. Instead, our models are a little more mundane and behind the scenes and a lot more code-based. Typically what we try to do, so I'm going to just back up and give you a broad overview of what transportation modeling is. There's really 4 things that we're trying to figure out with our transportation modeling, and they're kind of encapsulated by the traditional 4-step model. We're trying to figure out how much demand, how many trips are there going to be, where do people want to go, where do they want to travel, how do they want to get there, and which ways do they want to get there by. So this basically can be summarized by the 4 steps: trip generation, how many trips we want to we create, and that's kind of a function of your land use and your population. Where those trips want to go. Oh, and it's also trip generation. I should mention is also what kind of trip is it? Is it a work trip? Is it a shopping trip? Is it a recreational trip? Is it a school trip? So once you figure out what kind of trips and how many trips, you next have to figure out where are those trips going to go. So I'm going to go work over here, or I'm going to go shopping over here, or I'm going to go to the Friday seminar over here. And then once you figured out where you're going, how are you going to get there? Are you going to drive? Are you going to catch a ride with your buddy? Are you going to take transit? If you take transit, are you going to drive to a park and ride facility? Or are you going to walk out your front door and get on a bus? Are you going to take your bike? Or are you going to walk? And then finally, once we figure out how we're going to get there, we figure out what's the route that we're going to get there by. If we're driving, are we going to take the freeway or are we going to take the arterial? If we're taking transit, are we going to get on the local bus and take that to another local bus and transfer? Or are we going to walk a little further and get on the MAX and take that down to school? And it's this last step, trip assignment, that we're focusing on today. Now, and particularly on the auto side. So we'll just step back and let's talk about traffic assignment. So in traffic assignment, we're assigning vehicles to the roadway. And these are typically classified in our region one of 3 ways. SOV, or single occupancy vehicle, you're driving alone. HOV, high occupancy vehicle, you're driving with a friend. Hopefully it's a friend. And then truck, which is basically freight. And then we also do assignments for transit and bike and ped, but we're not really focusing on those today. So this is our modeling region. Again, it encompasses all of Washington, Clackamas, and Multnomah County, and includes Clark County. And we've broken it down further into these little analysis zones. These are kind of the spatial representation where we get trips from and to. In our region, there's about 2,200 of them. On top of that, we've overlaid a generalized network. So this is the auto network that we typically model in our system. It's pretty much, it doesn't have all the local streets in it, the little cul-de-sac or the street where your house or apartment may be located, but it has a lot of the collectors and above. So it'll have like the Alberta, and it'll have the Prescott, and it'll have the Skidmore, and the Division, the Hawthorne, etc. And so those little analysis zones are connected to this network, and this is what we use to assign our traffic. And the network has attributes associated with it, like number of lanes, the speed, and usually some sort of capacity, theoretical capacity. So there's basically three very broad resolutions of assignment models. We start at one end, which are the macro simulations, or the proxy here will be static assignments. These are deterministic models, meaning that you put the same inputs in, it does the same math, you get the same output. They're based on relationships between speed and density on your network. The trips are, you're not actually modeling individual vehicles, you're modeling aggregations of trips, and those aggregations usually cover pretty large time frames, so at least an hour. Typically, we look at 2 hours. And the vehicle classes, because we're not modeling individual vehicles, are all homogeneous. So all the SOVs look the same. You really don't know anything about the particular vehicle in an SOV class. Same with HOV in truck. Some of the pros about using these static assignments are that they have this thing called route choice capability. You can do multi-path assignments, and I'll show an example of that in a little bit. They're very well integrated with that four-step model I was talking about before. Static assignments have been around for a very long time. The theory goes way back, and so they've been tweaked and retweaked and retweaked, and so computationally they run very fast, and they work very well at a regional scale. Typical types of outputs, I think I discussed some of these before. We look at like differences in link volumes. We look at volume to capacity ratios to see if anything is approaching 1. Unfortunately, with these models, they often exceed 1. I'll talk about that in a little bit. And then we look at like speeds and travel times. So this is what I meant by multi-path assignment or route choice capability. This is an example of a trip between basically Pioneer Square and downtown Gresham. And you can see that this particular trip has identified 17 different paths or permutations of paths that can be taken. There's one that makes a lot of sense. It's along I-84, the freeway here, all the way down to the 230 or whatever that is out in Gresham, and then south. There's some that take, this looks like Division to go out there, and then there's a mix and match. If you look at the travel times, they're all pretty much relatively the same in the same ballpark. What's great about these assignments, though, because you can choose different paths, if we were to do something, say, on the band field here, like, say, eliminate some capacity, what we would see are vehicles shifting, vehicles that would be taking this, would shift to some of these other paths. Likewise, if we were to make an improvement here, we would see vehicles shift to these paths. And so that becomes an important part of our travel analysis, because we know that if you make an improvement or you make something worse somewhere, the impact isn't going to affect just the people there. It might have a wider impact. If you make this worse here, you're not just going to impact the people who are traveling on this route. Those people are going to come here, and that's going to slow down the people who were already here. And so you can kind of measure the system-wide impacts of your transportation plan. Some of the cons for using these static assignments is that the total demand is assigned regardless of capacity. So I won't go too much into this, but you can get volume to capacity ratios that exceed 1, which in theory shouldn't happen. It basically is saying you have more vehicles using the roadway than the roadway could possibly handle. But because you, typically if you were to see something like that, you should get massive gridlock. Your system should shut down. But in these static models, because of the way the math works, you won't see that. All the vehicles will assign. You may see some slow speeds, but you'll never get total gridlock. And also, there's no temporal information about your analysis period. So if you traveled at all, which we all have, you know that if you, for example, are leaving to go from school to home or work to home at 4 p.m., that trip looks a lot different than if you go at 5 p.m. When the peak period is really getting going. And 5 p.m. might look a lot different than 5:15 or 5:30. Unfortunately, with these static models, you don't really capture that. And so you're not picking up kind of like these nuances that help us figure out what's going on with our system. You can't pick up queue formation. You can't pick up bottlenecks that might be occurring and propagating upstream on a highway. You can't measure the duration of congestion, and you can't track individual vehicle profiles. So you can't look at like the impacts of policies like pricing. This is an example of some of those shortcomings. So on this road, on this series of roadway links here, the red represents areas where the volume far exceeds the capacity. So it's 1.0 or higher. And so if you actually saw this out in the real world, this would be completely jammed up. You would see speeds of 0, very close to 0. But over here on this side, this is the equivalent speed map. And actually, orange is I think the slowest color we see in that. It's hard to see the legend, but that's 20 miles per hour. And you see upstream here of that location, 30 miles per hour. Well, we know that just wouldn't happen if the roadway was completely jammed up. So that was one end of the spectrum for assignment models. On the other end, we have these things, microsimulations. So microsimulations are stochastic models, meaning that they have an element of randomness to them. And they're based on car following and driver behavior rules and infrastructure design. So they keep track of individual vehicles, and they have acceleration and deceleration associated with those vehicles. They have like gap acceptance. What kind of gap do I need between vehicles to make like a left-hand turn? What kind of gap do I want if I'm going to merge over? Is the person behind me being polite and backing up so I can merge in, or are they really aggressive and speeding up and not letting me in? That's what microsimulations are really good at modeling, basic driver behavior, what's happening in the real world. Because they're modeling individual vehicles, they're also modeling them in very small time periods. Oftentimes these things are updating at the sub-second level. And so they give you the opportunity to really see what's happening temporally during your analysis period. So you can see the difference between traveling at 4 p.m. versus 5 p.m. versus 5:15 or 5:30. And they are confined to roadway capacity, theoretical capacity, meaning if there's too many vehicles trying to use the roadway, you will get a bottleneck. You will see queuing or congestion forming and backing up. And you will get gridlock eventually if you have too much demand. So they're much better at modeling what's going on in the real world. So I've talked about some of those pros. Why don't we just... So here's some examples of microsimulations. This one down here in the lower left is a very simple microsimulation. I'll use this later for a little demonstration. It's just a roundabout. We have some vehicles kind of with their turn signals on using it. This is a more typical use of microsimulation. This is an intersection analysis. This is a single-point urban interchange. If you're a traffic engineer, this is like one of your favorite things out there, a SPUI. Lots of those up in Vancouver on I-5 and I-205. This microsimulation was probably created just for this small area. And then here, oops, I'll go back. This right here is just a screen capture of a very large microsimulation that was created during the I-5 replacement study, or the Columbia River Crossing, CRC, from about 10 years ago. And this was actually a pretty large microsimulation as microsimulations go. It was about a 4 or 5 mile long corridor, and it had all the traffic on I-5 using this bridge and coming all the way down to the Rose Quarter. So, but that that's a very large microsimulation. I'm going to skip some of that and go right here to some of the cons about microsimulation. They can be very time-consuming to develop and calibrate. Because there's so much information associated with them, and because they're so sensitive to what's occurring, you can spend a lot of time trying to make sure that you have all your signal timings at intersections very precise, that you're modeling driver behavior accurately. Driver behavior actually changes region to region. Some people in the Northwest might drive less aggressively than somebody in the Northeast, for example. They're very computationally intensive. So if you design a large microsimulation, it takes a long time to run, and you have to run it very many times. Because it's stochastic and it's random, you often run these things multiple times and then look at things like percentiles, like what was the median metric, or what was the 95th or 5th percentile. And oftentimes the vehicle paths are fixed in these models, meaning they don't have the ability to change paths. And I'll show that here in a second. So this is what I mean by that. Here's our little roundabout example again. And the green represents the paths for all the vehicles coming in at gate 1 and going to gate 4. So this handles fine. We know that the vehicles come in at gate 1 and they want to go to gate 4, and this is the route that they take. And then the microsimulation might figure out, okay, where are they going to wait for the other vehicle before they merge in, or when are they going to pull over, or when are they going to put on their signal? But if something were to happen right here, if there was to be a crash, or if their lane had been eliminated, or there's too much traffic, these vehicles don't have any other route to go. They have to wait. They can't choose to take some other route that's not in the microsimulation area. So this alternative path isn't available to them. And that becomes an issue when you're studying regional plans or scenarios, because you can't really capture the region-wide impacts outside of the immediate microsimulation area. It can also lead to issues like overestimation of delay or underestimation of speeds, because you're not truly representing behavior that people might follow, like changing their route. So what do? Well, as with anything, you merge the two and you take the best qualities of both. And that's how you get dynamic traffic assignment. This is in the middle. It's mesoscopic in scale, meaning middle, right? So what's DTA? I say mesosimulations, and dynamic traffic assignment is a type of mesosimulation, but for all intents and purposes, DTA will be mesosimulation. Well, they are models that are larger than microsimulations. They may not be quite as big as the full regional static models, but they're still pretty large. They maintain that route choice capability of the macro models. But at the same time, you're actually simulating individual vehicles continuously like the micro models. And so you might have a simplified version of the driver behavior. Maybe you don't have all those driver attributes like politeness and aggressiveness and willingness and gap acceptance. Well, gap acceptance is one of the things you can change, but usually it's generic across the entire population. But you're giving some kind of behavioral characteristics to the vehicles, and each vehicle is individual, so you can kind of keep track of what different characteristics of the vehicle as you're modeling, and they can be either deterministic or stochastic, and I'll show reasons later why that's important. The vehicles, like micromodels, are limited to the capacity of your roadway network. Traffic builds through time. You get the buildup of bottlenecks and queues, and you can keep track of those temporal differences in trips that happen at 4 p.m. or 5 p.m. or 5:15. And they're great because they allow us to gather data and start looking at things like where is congestion occurring, how much of our system does that congestion impact, how long does that congestion last, and we can start to analyze policies like congestion management through pricing. Things like priced HOV lanes, like they have in other regions, like in Seattle, where if you're driving alone, you have the option to get into the HOV lane and pay basically a toll in order to use it. You can measure things like reliability, and we'll talk about that here in a bit too. And they help you do more detailed emissions and greenhouse gas analysis. So I'm going to show right now, what do these models look like? What do some of these DTAs look like? So let's see. Not that one, this one here. Okay. So this is a crude animation. What you see is traffic building through time on our regional network. You can see this is the bandwidths are volume, and so you see those facilities with the large volumes tend to be our freeways, and you kind of see like pulsating widths of those bandwidths over time. It just shows that the volumes are changing over time. There's not much you can really gather from that. You can kind of you get a sense for what your network looks like. But we can extract data from that, and that data allows us to do things like this. So what I have here is loop detector data that's basically volume over a certain time period. And so you have these big metal rings out in the freeways, and they're counting the number of vehicles that are crossing over them. This blue line is the actual data, so this is empirical data that we've collected. This black line represents the volume that our static model says should be at that particular location right here. And you can see it's holding steady at 1,400 vehicles per hour from 3 p.m. 1,400, vehicles per hour per lane from 3 p.m. to 6 p.m. essentially. And there's no change because you only get an average from the static model. With our DTA, this red line, you can see we're actually doing a pretty good job of matching the flows across this location. It starts out lower at 3 p.m. as we would expect, and as you move through, up to and through your peak period, your volumes increase. So that's useful. Now, kind of an inverse of that is travel time. So this is a corridor. This is the I-5 corridor from I-84 up to basically northbound across the I-5 bridge to SR-14 in Vancouver. Again, a single static travel time from 4 p.m. to 6 p.m. of roughly 23 minutes in this corridor. Our DTA is showing a time of 19 minutes at 4 p.m. and a max of around 27 or 28 minutes in the peak of the peak, which more closely matches what we would see in the real world. Okay, so that's nice. Now we have a better sense for how our system is working and kind of when it's starting to get congested or when volumes are increasing. So how can we use that to analyze an actual project? So here is an example of using that randomness in the DTA to measure reliability. And by reliability, I mean it's basically variability. How much does the travel time differ day to day? As we all know, you could leave at 5 p.m. one day and make a trip, and your travel time would be different if you left 5 p.m. the other day, which might be different than the next day and the next day. And after a while, you get a range of travel times, and something that's highly reliable, that range would be very close. Something that's unreliable or highly variable, you'd have a huge range of travel times. So here we're analyzing essentially a freeway where you have 3 lanes and you have an off-ramp. You drop a lane between that and then the on-ramp, and then it picks up again, versus just adding a lane that travels through right here. So typically what we would do is take our scenario where we have the drop lane, we run our model a statistically significant number of times, let's say 20 times here. We figure out what the 5th and 95th percentile times are, and we have some other based on our model runs, and we can kind of produce an area. That area is right here, and this kind of shows you where your variability is, your reliability. So areas where you have a big gap, less reliable. Areas where you have a small gap, much more reliable. We can do the same for our scenario where we've built a link and added a lane, and now we can transpose these on top of each other. And what this tells us is a lot of things. One, when you add that link there, not only are you improving the travel times at pretty much all times of the day, as you can see, the blue is always less than the red here on the x-axis, y-axis, one of these axes, axi. But it's also narrower in a lot of the areas here, which means it's less variable or more reliable. And even in the areas where it's less reliable, where you have a bigger gap, even the 95th percentile is better than most of the travel times you might experience in the bad scenario. So this is just kind of a new way of looking at dynamic output. Let's look at some other versions here. Okay, so, oops. Okay. And is it F11? Window, view, full screen, Control L. Okay, so this is a very similar plot. What I like about this is an animated PDF. I don't know if you've ever seen these before, but you can actually add animations to PDFs. And this is those individual travel days. So the dark blue and the dark red are your different scenarios, and then the lighter are your past scenarios. And you can start to see how they change. And then we'll just play this to the end. So you can kind of see a lot of the variability there. And then in the end, you can analyze your 5th and 95th percentiles. And what's nice about this is if you're analyzing this day by day, you really get a sense for how much variability there really is in each of your travel days. So this is travel time up here, and this is speed, which is pretty much an inverse of travel time. So that's one nice output that we've used. This here is kind of another. Well, I'll play this. So this is vehicle hours of delay accumulated at various intersections between two scenarios. And delay is basically defined as any time, the amount of time spent where the speed at a location is less than 60% of the free flow or posted speed limit. And so what you see here are two scenarios, and these middle links here, you'll see that there's more delay occurring in scenario 1, and especially once we get towards the end of our analysis period, you'll see it speeds up a lot more than the other one. So it kind of gives you a sense of where the delay is occurring between the two scenarios, how much delay is occurring, and when is it occurring. All right. Okay. So, yeah, I'll get into this. This is a little bit more complex analysis using DTA. So this was actually based on some research we did where we had both a dynamic traffic assignment and a dynamic transit assignment. And I won't get into too much detail about what a dynamic transit assignment is, but let's just say that it does a better job of modeling transit vehicles in traffic and shows them queuing up or bunching up if there's a lot of congestion and spreading apart if one bus gets stuck somewhere, or if you show up at a bus stop and there's a lot of people there and a bus comes up and there's only space for 2, so only 2 people can get on and not everybody can board. That bus will go by and you can't get on. It's a cool tool. It's still under development quite a bit, but in this particular research study, we looked at some scenarios where we added variable message signs. So these are message signs that are up above the freeway that give you some sort of travel information. And I'm sure you've seen these before. They might say travel time between here and there is 10 minutes now, and the next day you might see it might be 15 minutes. Or sometimes these will tell you, like, hey, there's an accident at point X, take route Y or something. But basically the idea is they provide the traveler information, and they can make more efficient decisions based on that, routing decisions. So it's a little hard to see here in these graphics, but we applied these variable message size to 3 scenarios where we had bus BRT running on basically Barber Boulevard. And let me go back real quick. This was done on Barber Boulevard and I-5, and what's nice about this particular application is that these 2 facilities in this location are right next to each other, and there's a lot of interchange. So you have the ability to change your route at a lot of different points here. So this was a good location to kind of test this scenario. So BRT, we're testing in this first scenario, we're testing it in mixed traffic. So the buses are behind the cars here. They're running with traffic. So if there's congestion with traffic, the buses are going to get slowed down. Typically when you see that, the transit user doesn't really see very much benefit to taking transit relative to autos. In this particular scenario, the buses are in their own right-of-way, and they've been squeezed in between the autos here. So the buses have the benefit of free flow. They're not stuck in traffic with the autos, and the autos have the benefit that they have maximum capacity, and they're not dealing with buses. In this particular scenario, the buses are again in their own right-of-way, but we've done that by taking away a lane for the autos. So what you've done here is you've made the buses really attractive, and you made the autos a little less attractive because they have less space to operate in, and so their travel times are longer. And in all cases, VMS and no VMS, we see a progressive increase in the transit mode. But when we put in VMS, which is something that we can measure the impact with these DTAs, while we still see that progression, it's not quite as large. And even in the best case scenario here for transit, you're barely surpassing the worst case scenario without the VMS in there. So if you're a decision maker, or it gives you more information to kind of help you with your policies. Is your policy for this particular corridor that we want to maximize the transit mode share? We want to get as many people on transit as possible? Or is your decision, we want to maximize the throughput of all people through this corridor, so we'll add transit, but we'll also make the autos more effective, and we might not get as many people in transit, but maybe the system operates more efficiently. So DTA kind of allows us to look at things like that. So finally, let's look at, I think it's this one here. Okay. Nope, wrong one. We looked at that. Here we go. Okay, this is my favorite one here. So remember I showed that little simulation before at the very beginning that was actually SimCity. Well, this is where DTA has started to evolve to. So this is the latest in our DTA tools, and this is actually a lane-based DTA. And you'll see that as we zoom in here. You can actually see individual vehicles. So this is actual vehicles traveling on the roadway in the lanes. You can see some vehicles queuing here, merging here from the ramp, and it's having an impact. You can see these vehicles are bunching up and slowing down. So this is I-205 out in like the Foster Lentz area, and now we're pulling up. I think we're coming up towards, I'm not sure if that's Division or where we're at exactly here, but it's out in that general area. This was a DTA that we put together for a small project looking at the PAL Division BRT study. And it really wasn't used for much more than interacting between our macro models and our micro models. But what I like about this particular tool is that it's showing you some of the capabilities of DTA. The color here shows you timing. So let's see, maybe I can pause this in a second. We'll let this scan over. Okay, so here's Foster at PAL. So the green here is showing you the phasing. These are the phases that are allowed to go right now. So all these vehicles here just got a green light, and so they're going to be able to make their left turn, or they're going to be able to go straight. And the vehicles here where there's the little red lines, they have a red light, so they're just bunching up. And so we can see not only vehicles going, but we can see people queuing up into their respective lanes. If there's a turn bay there, they'll queue up in the turn bay and wait for the light to turn red for them. It also shows you these individual vehicles. This is kind of the future of where DTA is going. Someday, those individual vehicles will actually be tied to individual people that we're simulating, and we'll know things about those people. We'll know what kind of job they have. This isn't Big Brother. This isn't. We're not going to tie these to actual people. These are forecasted people, but we'll know who's in the car. Do they have a child that they're taking to daycare in the car? Is there nobody in the car? We'll know a lot of different characteristics. I'm going to play that again because I really like this. I think our next steps are to link some really advanced models to this type of a model, and at that point we'll really be able to say, okay, this is Susie in this car right here, and we'll be able to track her entire trip to work or to school. And we'll be able to do it multiple times, so we'll see how it varies day to day. And then we'll make a change somewhere. We'll increase capacity on a highway somewhere. We'll add some new bike paths, and we'll be able to see how Susie makes decisions. Does she decide to ride a bike because we've improved the bike path, or does she decide to drive? And if so, how did her trip improve? And so those are kind of the next steps with DTA in our models. And it's a pretty exciting time, actually. It's been a long time coming for that stuff. So I think, yep, that's about it. We'll continue applying our DTA at corridor level studies. We'll be implementing it. We're slowly building these things out to use in larger and larger regional studies. We still need to refine that transit component of DTA, but there's a lot of really smart people who are working on that type of stuff, and so it shouldn't be too long until we have that. We'll integrate this with our demand models. We have an activity-based model that'll help us kind of more discreetly model individuals in our region, and then we'll do some more advanced emissions analysis with these types of tools. And eventually, someday, those macro models that I started off with will be a relic of the past. I think we're actually getting to a point where DTA is becoming easy enough to implement that it'll basically be the standard tool. So with that, I'm happy to take any questions.
So when you go up from the micro level where you have people like, you have all these variables that people like engage in, it controls like where they're at on the assignment. Do you lose any of that when you go up to the meso level?
Absolutely, yeah, you do. So you still want to use the micro level when you get down to like really detailed operational analysis. You want to look at what the impact of different signal timing plans is, or you want to look at design characteristics, like how much merge lane do I need at this particular interchange. You want that micro level because it provides you can give each individual vehicle different characteristics, much like everybody is kind of different and they have their own characteristics. At the meso or meso level, you're kind of putting generic characteristics on those people, so everybody has the same gap acceptance. Everybody kind of accelerates and decelerates at the same rate. So they're good for doing a slightly higher level analysis, but they're not so good if you really want to get into, like, if you're really like trying to figure out what should our signal timing plans be, or what should our final design look like in this particular location. They're probably still a little rough for that.
So does like that loss of like that randomness you get by just sort of averaging out these variables, how much does that impact the meso level of the meso level?
It's becoming less and less because they're making these tools more sophisticated every day. But typically what we do is we distinguish how we're using those tools. So we're not using the meso level for a highly detailed operational analysis. We're using that for kind of a higher level, not quite sketch level analysis, but something where we don't need as much, where there's some room for like some generalization. So really, at the end of the day, it's about picking the best tool for the level of analysis that you want. And you take into considerations not only kind of the data you want to look at, but also how much time and budget you have to look at that, recognizing that with less time and budget, you probably get less accurate data. So.
And sorry, so second quick question. Those variable message signs, they made the traffic impact, they made things worse than not having them?
Well, it depends on how you define worse. If you're a transit advocate, you might say it made things worse because it decreased the transit mode share relative to a non-variable message size scenario. But if the whole purpose of making improvements in a corridor is to reduce congestion and is to make the corridor travel make it more efficient, maybe increase speeds so there's not as many emissions or that type of thing. While you might not be getting as many people on transit, you might be improving the speeds of autos. You're still getting some people on transit. You're getting people through the corridor more efficiently as a whole. So really, it depends on what your policy goals are. And this just kind of helps. This just provides additional, maybe even like information that makes the decision more complex in a way. So
it's like a case of people like they have just enough information to like sort of screw things up because everyone sees 15 minutes, let's take the other route, and then everyone leaves and take the other route and sort of just screws it up. That's what it looks like to me. It just I don't know.
Yeah. I mean, that certainly could happen, and so there's ways to test that. So you can say you can test that. So you do these one-shot assignments that, like, if there's a crash one day, how do people react to it? And they might all shift to another route and screw that up for everybody. But if there's crashes every day that happen at the same location, eventually people kind of figure out, like, well, there may be a crash. I could divert, but if I do that, everybody else is going to divert, so I'm going to stay on my own path. And, yeah. Good questions. Yeah.
Can you talk a little bit more about how the dynamic model is integrated with the air quality?
Yeah, so that's still yet to be done.
Okay.
But typically what we do with air quality is we have some programs that have been developed by the Environmental Protection Agency, EPA, and they pretty much, what they kind of tell, they have inputs like what your vehicle fleet mix looks like for your area, what are some of like the environmental conditions of your area, what's the type of gas that vehicles use, how do people drive, and they come up with these emission rates that are basically, this is the amount of pollutant or emissions that vehicles are putting out at this particular speed band. And so in the past, what we've done is using these static models, we can kind of figure out, okay, there's this many vehicles in this speed bin, and there's this many vehicles in this speed bin. In actuality, emissions aren't discrete like that. They're much more dynamic. So a vehicle starting up is going to emit different emissions and different amounts of those emissions than a vehicle that's running at 50 miles per hour. Likewise, a vehicle going at 30 is going to have different emission rates than a vehicle at 50. So these tools have been set up in a way that eventually you'll be able to plug in those individual vehicles and keep track of their speed profile over their entire journey and apply these very kind of disaggregate emissions rates to them. And so I think you'll get a better idea of your actual inventory of emissions.
Cool.
Yeah, sure. Yes.
Great. And could this be used to model bike flow?
Yeah. So one of the things about bike and pedestrians, one of the big differences between bike and pedestrian models from the auto models and even the transit models is that we don't ever consider capacity constraints, meaning that we don't think that, I mean, there's obvious examples in Portland, like if you're on North Williams at rush hour, there's a ton of people there, and it does have an impact on how fast you might be able to ride your bike. But in general, we don't look at those types of capacity constraints. So instead, we look at just the path that people are taking, and we decide, we have attributes for those paths. Like, is there a slope? Is there a bike lane present? Is there traffic that's next to you? Is there a multi-use bike path that you can use? And so we have different models and different ways of kind of assigning those particular trips. Eventually, yeah, we could. I mean, we certainly could model the bike stuff dynamically. I don't know if I've seen it done yet, but there may be a compelling reason to do it. Yeah. Yeah.
Great presentation. My question is a bit more practical, and we are lucky in the region that we have a lot of data in Portal, and since 2004, archive data that is pretty good for freeways and even some arterials. So as you move from the traditional less data hungry models to DTA, what is the metro experience in terms of, is there enough data when you want to go to the arterial level for calibration, for looking at the flow density curves and so on, the speeds? And maybe if there is no data, what do you guys do in terms of what kind of rule of thumb? So how do you?
That's a good question. So the question is, what kind of data exists out there for us to basically calibrate and validate these models, and what kind of data is lacking, and what do we do when we find data lacking? And we're fortunate in the Portland region because we do have some pretty amazing data sources. The Portal Freeway Count Archive is a great resource. And we rely on that quite a bit when we're validating these models. So you have these loop detectors in the roadways, and they're constantly counting the number of vehicles crossing them, and they can calculate occupancy, like how long are the vehicles on there. You can calculate speeds, interpolate speeds from those. And because they're constantly collecting the data, you can build a temporal profile from those. So we've done that quite a bit, and we've actually used those to calculate some of the volume delay curves that we use for our assignments, so basically how vehicles respond as congestion builds up. One of the things that we have had trouble validating against is travel times. And so there are some data sources out there that help you pick out, that help you kind of determine what the travel times are, like through, let's just pick a corridor. Let's say I-5 North from the Rose Quarter up to Vancouver. There are data sources out there like INREX and HERE data that are basically collections of GPS point data from vehicles that are constantly putting out. And from that data, they can figure out a speed profile, a travel time profile for that corridor over any time slice of the day. As long as there's enough samples, they can get close. Unfortunately, those data sets for our region, just the current ones don't seem, they can be hit or miss. There's gaps in the data sometimes. The way that these are all third party, so they're algorithms that they use to kind of aggregate the data, or can be kind of black boxish. And sometimes we'll look at a corridor and say, that doesn't look right. That it looks like the peak period, like the worst congestion times are happening like an hour too early, just knowing our region. So I think we've struggled a little bit in some of our travel time data. Now that's improving. And I think it's not just us who struggle with that. That's a national thing. So my hope is that, travel time data is probably what we lack and probably what we need the most. That's probably where our blind spot is right now. But the portal data is excellent, and it's invaluable, and we're really fortunate to have that. Yeah, you mean?
Number of questions, but since you're showing this, I'll probably ask this question. How do you feed this back to the mode choice? Are you feeding this back to the mode choice model?
Yeah, so in this particular research project, we actually did feedback. And I can get really technical, probably more technical than necessary for this seminar. But essentially what we ended up doing was we were using a DTA package called Dynasty, and we were using a dynamic traffic assignment tool called Fast Trips, and they were integrated. And we had built in a reliability measurement into both of those. And at the end of the day, we ended up converting that reliability to a travel time equivalent, and then using that as an additional skim that we fed back into mode choice. And we also focus at just the corridor level. So we were looking at mode choice impacts just within the corridor. So the Sharp 35 research, which is out there, kind of goes into more detail about how that works. But yeah, I think it was a pretty cool implementation. It was also one of the first national implementations of DTA with a 4-step travel demand model.
Very interesting, but also you kind of think it as if it's a very short-term impact. It's kind of a time scale where people are probably thinking mode choice as a longer time scale.
Exactly, yeah.
So that's certainly it's interesting to look at the effect, but it's probably not the actual or realistic impact that people are seeing. That's probably why there are questions about why this is a bit counterintuitive.
Yeah. Well, I will say, yeah, this was a research project. It was much more like proof of concept than anything. This was not like a corridor study by any means. We did run the model, though, at least 20 times. So, this is basically the other thing is that you assume with this you're providing perfect information to the traveler, and 100% of your travelers are taking advantage of that. So it's kind of like this user equilibrium built into the system equilibrium, actually, but kind of built into your assignment. And I agree, it's probably not quite realistic. Also, if you look at those mode shares, this is kind of lying with numbers. It's not a very big difference. It might well be within the margin of error since we're using stochastic models for this. So, although the trends seem to be, at the same, there's similar trends there. So, it's not all randomness. Sure.
Is it possible to define the vehicle class in the model? And if it's yes, is it possible to set the value of time for each class?
Yeah, exactly. So that's a really good point right there. so being able to model individual vehicles, we can then, I talked about how we could say, okay, this vehicle has, so-and-so in it. It's got Susie and it's got her friend Matt in there. We can then model, well, what are the attributes of Susie? Well, she has this value of time. She's willing to pay this amount of money to save this amount of time. Or maybe, Max, who is in a vehicle behind, has a lower value of time, so he's willing to pay less money to save time. So if you do add some sort of pricing scenario, if you add like a hot lane, so an HOV lane with a toll in it, Susie might be willing to pay some money to get into that hot lane to save some time to get to work. Whereas Max would be like, I'm not in a big hurry today. Maybe I'm not going to work. Maybe I'm just going to meet some friends somewhere at a restaurant. So, yeah, exactly. That's the benefit of being able to model individual vehicles is you can model the attributes of the people inside those vehicles and really get detailed in kind of like pricing studies and other things.
The model for 20 times. So until how many times you run until you get to the solid point that you're resolving?
Yeah, so where they're converged and they're not bouncing around too much. But, so it depends on the model. It depends on the size of your area. It depends on the level of congestion. With Dynasty, which is the tool we use with the stochasticity in it that allows us to do that kind of reliability analysis, it might be 50 times, 50 iterations. But if it was a really congested network, it might be 100 times. Now, one of the emerging kind of discussion points now in DTA, I guess this has been around for a while, but it's something that people are thinking a lot more about now, is if you have randomness, you start, there's this thing called gap acceptance, and it's how much your network changes per iteration. And that goes down slowly, and then it kind of levels off. Well, in stochastic models, it bounces around. And so the question is, well, you're never really fully converging. So at what point do you decide that you're converged well enough? And what does that bouncing around even mean at the bottom? I mean, when I talk about randomness in the models, it's usually things like departure time. Like I'm supposed to leave at 5 o'clock, but instead I leave at 5:02 one day, or I might leave at 5:03, or at 4:59. Or it might be I'm coming up to a light, it's turning yellow. Do I accelerate through it, or do I hold back and do I stop? So that's what some of the randomness is accounting for. But is that all the randomness that's being accounted for in that bouncing around? And are there things that we're not accounting for? So, yeah, there's a lot of research that's going into kind of that stochasticity of the models.
Great presentation. Just a question about using Dynasty and this model. Was there any specific reason over? I think Dynasty when the facility is over capacity, it's macroscopic. If I'm not wrong, then it has this like Dynasmart P and all the DTA lie the same. The thing that when they're overly congested, they get macroscopic, and they sometimes don't do a very good job modeling over congested conditions. But other tools such as vSIM DTA or INRO or AIMSON, when they are over capacity, they are also micro level, which they have car following and the driver behavior part. Was there any reason selecting Dynasty over those? I know that it's time and budget, so probably.
Yeah, well, it also depends on what kind of analysis you want to do. So if you want to do a stochastic analysis, we're comfortable with Dynasty. That's the product that we have in-house and we'll use. We also use Dynamec, which is more kind of like micro-simulation light. I think you probably have more knowledge about how they're actually behaving at like near capacity, but one of the things that I can say from more of a practitioner's standpoint is one of the things we do like about the new DTA tools out there is that they do tend at super congested conditions tend to relax some of their constraints a little bit. So this might be Dynasty running at a macroscopic level. The new versions of Dynamec are doing something similar. Basically what this means is that the model isn't, when you get towards capacity, especially on early iterations of demand that you haven't calibrated, your model could just seize up completely and nothing goes anywhere, and it's just frozen, and you can't figure out, is it a network coding issue somewhere? Is it a demand issue somewhere? Make it very complex. But with these new tools, because they do relax some of the parameters on those congested conditions, it kind of says, okay, don't worry about this too much on this particular iteration. Let's just try and find some routes, and we'll try to equilibrate on subsequent iterations, and the hope is that eventually the path-finding algorithms will find paths for the vehicles that don't lead to so much congestion, that are more realistic, in which case you can rely more on the micro aspects. That's probably, I'm sure there's some developers out there who would roll their eyes at me for putting it in those terms, but that's kind of the way I understand it.
Is it possible for static assignment to analyze bottleneck or queue formation?
Not really, because unfortunately, one of the things I didn't talk about is not only is like when you look at like a static assignment output, not only is the output basically generalized for the entire analysis time period. So if you're looking at a 4 to 6 p.m. Assignment and you see a speed, that's like the average speed for that entire assignment. But it's also the attribute is for that entire link that you might analyze. So let's see if I can find an example real quick. Okay, so on this example, you might have a bottleneck that's starting at this location that propagates upstream to this point and then dissipates, but you can't tell that here because this entire link is given the attributes of what's happening on average at this location. So you really have, you can kind of identify, you know that there's a trouble spot on this link somewhere, but you don't know where it exists on the link, how far it extends, how long it lasts. And furthermore, if it truly did go all the way to the end of this link, it would certainly impact the links upstream of it. And static assignments just do a really bad job of basically propagating upstream links. So there's very little relationship between this link here and this link here other than travel time impacting path choice.
Went over 1 minute over the time. So,
Thank you. Great questions, everybody. Those were good questions.